Good morning. I think I have started the recording. Let me just check that. Yes. So we will start the class today with a discussion about cyclopentadienyl complexes. Cyclopentadienyl complexes are extremely popular. They are probably next to carbon monoxide complexes. And as you would have seen from the various lectures, that there are so many complexes that I had to introduce you to, where I just noted the fact that a CP ring was a cyclopentadienyl ring was attached to the metal, and we did not discuss the chemistry or the bonding or the mode by which it is formed. But we have already seen several complexes of this form. In fact, cyclopentadienyl complexes, rather than carbon monoxide complexes, revolutionized organometallic chemistry. So you might be wondering why and what. I told you that carbonyl complexes were known very early in the game. In other words, even a century before organometallic chemistry became popular, carbonyl complexes were used or were there in the chemical field. But then people did not take note of organometallic chemistry as a separate area of research, and it was only when cyclopentadienyl complexes came into the literature that organometallic chemistry really exploded as a separate area of research. Today we are going to talk about sandwich compounds, and we'll discuss how this particular name came about. So just to make note of the lecture, these type of complexes are there in a variety of forms, extremely common in the literature, as I told you, but they also come in various shapes and sizes. Here on the screen I have for you on the screen about 6 different ways by which organometallic compounds are there with cyclopentadienyl groups, and you can see that they are indeed varied. So the type of structure is not unique to this which we associate with ferrocene. So I have to tell you the way in which it was discovered. It was indeed an accidental discovery. It was not in fact a planned or straightforward discovery that led to ferrocene. In 1951, in fact, this should also be 1951, July and Pawson and Keeley in August, they submitted 2 papers. Both of them were in ferrocene. This was a high temperature reaction between cyclopentadiene and iron metal in metal oxide catalyst 300 degrees, and they got a compound which analyzed to CP2Fe. Pawson and Keeley, on the other hand, were actually trying to make CPMG, were reacting, CPMGBr they were reacting these two with the hope that they will make bisfulvalene. This is what they wanted to make. And the idea was CP is actually C5H5 minus. And if you oxidize this with FeCl3, you would end up with C5H5 dot, that is the radical, plus FeCl2. And C5H5 dot could be further coupled to this species, and this species can be oxidized with FeCl3 again to give you bisfulvalene. So this was in fact a very clever way of making fulvalene. It was an ingenious strategy. I do not know what these people were up to, but nevertheless, both of them published a paper saying that they got an orange compound, which was very stable. In this case, it was obviously stable at 300 degrees. And these people found that it was what they wanted was an organic compound, but there was a persistent ion sitting there which they could not remove. They assigned the structure promptly to bisfulvalene ion. So this is the structure they assigned it to. Now, it turns out that when this paper was published, there was a bit of an uncomfortable feeling. It took a long time to publish, actually. It was not a very quick acceptance, because iron in this type of a geometry is not really known. It's not likely to be stable. People know it as FeH2O6 2 plus, that is fine, but then you have octahedral coordination. I think I messed up. So the properties that you expect for a compound like this did not match the properties of the compound that they have reported. At this time, Wilkinson was actually in working in Harvard, and he was working on some nuclear chemistry. He was not an organometallic chemist. So he was working on some nuclear chemistry, from what I read. And he read this paper and he discussed it with Woodward. Woodward was in fact quite a genius, and he realized that the structure of this molecule, they were both going for lunch, lunch to the Harvard faculty club, I guess, and they found, and they discussed this, and then Wilkinson said that this is the structure that they proposed, but he was not happy with the structure, and Woodward immediately said that this is probably a structure in which the ion was in between two cyclopentadienyl groups, and as they were going for lunch to have a sandwich, this name stuck. So the sandwich name actually came up because they discussed it during lunchtime. That's really a fact. So at the same time, Fischer in Germany, I think that was Munich, he was looking at the structure of this compound and he used X-ray crystallography. In those days, the resolution was not so good. The quick form that he got was this particular regions of electron density. You measure the location of electron density, if you remember X-ray crystallography, and he proposed the name a double cone structure. Essentially, the structure that Wilkinson proposed and what Fisher proposed were identical. They said that this is like a double cone with the iron atom at this particular point. Of course, in the Wilkinson proposed structure, the iron was exactly in the same place and it had two CP rings. So you can see that these two people proposed the same structure. Wilkinson was quite fascinated by this chemistry and he switched to organometallics as his main field of interest. I think after that there are no hints of him working in nuclear chemistry that he was doing at that particular time. Okay, let me see what I have. This structure that has been proposed. This structure that has been proposed is I'm not showing you the structure. Just one second. You should be able to see the structure of ferrocene on the screen. This is the structure. In fact, this structure is such that the top ring and the bottom ring are not exactly superimposed. They are staggered. So if I were to look at this structure did not very clearly specify, but here I have indicated it to you as if it is staggered, but their proposal may not have been that particularly. Now, the reason why CP is staggered is not so straightforward, because the energy difference between the staggered forms and the eclipsed forms, if I can call, I think we can stick to the eclipsed form of the structure. So what I am referring to is this is the top ring, and if I write the bottom ring in a slightly exaggerated size, then I have iron in the center. So this would be the staggered form, and this would be the eclipsed form. It's not so difficult to visualize these two, but why these two forms are so close in energy is something that will come up once we look at the electronic structure. Cp minus is not the only ligand which binds like this. Pentamethyl cyclopentadienyl group is also called Cp star. Now, it's not exactly clear why that star came about, but is definitely a star ligand, just like I would call NHC a star ligand. Cp pentamethyl cyclopentadienyl is also an extremely popular ligand, and the reason is that these hydrogens on the cyclopentadienyl group are not so innocent. In other words, they tend to react. Okay, so these groups tend to react. As a result, I should not have drawn. Like this. So these hydrogens are reactive. So Cp pentamethyl cyclopentadienyl group, Cp star, is a good substitute for Cp, and essentially this turns out to be quite popular. If you look at the previous lecture where we talked about the allyl group, this seems to be a combination of allyl plus a double bond. And in fact, there is some indication that the cyclopentadienyl group can behave as if it was a combination of the allyl plus the alkene. It can behave as if it is like something like that. Now, if you look at the way in which it is represented, one usually writes it as eta 5, C5, R5. That is the best representation for this form in structural notation, and in a drawing it would be indicated with a center. Now let me come to this question of perfectly staggered and perfectly eclipsed forms of metallocenes. This is intimately connected with the electronic structure of metallocene, and we need to take a look at this. I will show you the electronic structure, some of these orbitals, but you can have a simple way by which you can match the orbitals of the cyclopentadienyl group and the iron atom, and you will find that there are orbitals which are matched perfectly in order to achieve a nice structure that can either be D5d or D5h. The symmetry of the staggered form is D5d, and the symmetry of the eclipsed form is D5h, if you have studied symmetry. Okay, so here is the structure of the D5d form. Okay, you see that the two rings have been drawn. This is from Elschenbroid's book. And Salzer, and you will notice that there are totally let me see, there would be 5 pi type orbitals on each Cp minus. Each Cp minus would have 5 pi type orbitals, right? And these rings can be combined in different ways. For example, in the bottommost form, this is the lowest energy pi molecular orbital that you can form with one Cp minus, and this can be combined in 2 different ways. In one way, you would orient the 2 forms such that the same face is looking at the iron atom. So here we have noted it as if it is shaded. So the 2 shaded lobes of each Cp minus, this is Cp minus, this is Cp minus, both of them are the lowest energy orbitals. They are facing the same side, and the iron in fact is looking at the same face. Then of course the symmetrical s orbital and the dz squared orbital, which also has the same face on both sides, can form a bonding combination with this A1G type orbital. So if on the other hand, if I have the opposite faces coming together or pointed towards each other, then the ion can interact with the pz orbital. Now it turns out that because you have 2 Cp minus rings, you will have both combinations. So in other words, the lowest energy orbital of Cp minus will have this and this combination, and you can interact, both of them will be filled. Okay, I hope all of you remember the phrase diagram. If I have any pi system, I can draw the pi system inside circumscribe a circle, and in fact I can get both the energy and the distribution right. So I will have degenerate orbitals after this. The lowest energy orbital, however, would be unique, and that is the lowest energy orbital is the one which is given here. After this, of course, there are degenerate orbitals. These degenerate orbitals on the cyclopentadienyl ring will also combine in a plus and minus fashion. So those are the orbitals which are shown here, right? They are combined with the same side or the opposite face. And similarly here also, each one of these pi-type orbitals on cyclopentadienyl ring can be combined in plus or minus fashion, and each one of them, you will notice that each one of them can combine with either the dxz or the px or the p-type orbital. You will also notice that the dxz orbital is pointed towards the cyclopentadienyl ligands. So in other words, if I have the ion in the origin, I have ion at the origin on the plus xy plane, parallel to the xy plane, on the plus z, suppose I take it as 1.5 angstroms along the plus z axis. If I draw the CP ring and minus 1.5, I draw another CP ring, then you can see immediately that the dxz, dyz orbitals will be suited for interacting with these two combinations. So in this fashion, you can match the orbitals. These orbitals have better overlap. These orbitals have only lateral overlap. They are only lateral overlap because the plane on which this is lying, the px and the py, are on the xy plane. Whereas the orbitals that we are talking about here, the pi-type orbitals on the cyclopentadienyl, are along the z-axis, are parallel to the z-axis. So the type of interaction that you get for the dxz and the dyz is much better than the overlap that you have here. So here you have poor overlap. Similarly, you have the dxy and the dx squared minus y squared interacting with the highest energy orbitals. Now you'll notice that the Cp minus has got, let me this gets entangled. Let me just get another color to indicate the electrons. So here you have filled, here I have it filled. I have 6 electrons on each of the Cp minus rings. So up to this point, 3 plus 3, 6, up to this point, they are filled orbitals on the ligand. Ligand orbitals and filled. Okay, so you need empty orbitals on the metal to accept these electrons, and so the dz squared, dxz, dyz, if these 3 orbitals are empty, then obviously you would have sufficient space to accommodate the ligand electrons that are coming in from the 2 Cp minus ring systems which are above and below the plane of the above and below the ion atom. On the other hand, these 2 orbitals are empty, and so you can have 2 of the d orbitals filled. 2 of the d orbitals at least can be filled, and so they can have electrons pumped in from the ligand, from the metal into the empty ligand orbitals. This is empty on the ligand, and so you can push in electron density into them from the metal orbitals. So the DCD model that we have been talking about all along in organometallic chemistry can be applied to the ferrocene ring system also. And if you look at, let me see if I have, yes. If you look at the energy level diagram, these are the ligand orbitals I have drawn fortunately on the same side. I will have up to this point filled. I am filling up the electrons quickly, and these are now ligand electrons which are sitting on the ferrocene molecular orbital energy diagram. So those are colored in violet, and I can have a maximum of 6 electrons. If I want to have an 18 electron system, I can have a maximum of 6 electrons. And let's put that in a slightly different color in the electrons from iron. You'll notice that iron is having +2 oxidation state because ferrocene is neutral. So 6 electrons are there, and these 6 electrons can be filled in these orbitals. In fact, this is now an 18 electron system. This is the energy level diagram that you get from some MO calculations, and was sufficient to explain the magnetic and EPR properties of many, I should say magnetic, magnetic already said, EPR and magnetic properties, optical properties, optical, magnetic and EPR properties of several metallocenes. You'll notice that I'm using the word metallocenes, not just iron. Iron is diamagnetic, and there is no controversy about it. Whereas when you do the same synthetic procedure with other metals, quickly Fisher and Wilkinson came back to the UK. He was in Imperial College London when he received the Nobel Prize along with Fisher for their famous Metallocene research. They made every metal MCP2 that you can think of in the periodic table. So basically there was a race between Fisher and Wilkinson, and they made, it's famously told that both Fisher and Wilkinson would meet at conferences and decide which metals, who would be dealing with which metals, but they never kept their word. Each one of them went after the whole periodic table. So they made several cyclopentadienyl complexes, and all of them could be explained using this molecular orbital diagram and the type of bonding that is known, that is now popularly known as a sandwich structure. Now let me just show you I think I showed you the ferrocene structure. That was the perfectly staggered structure, but let me also show you, this is vanadocene. Okay, this is vanadocene. That is also staggered. Okay.
Sorry, sir, but is it visible to others? I can't see it.
Oh, okay. Yeah, I seem to have lost. Are you able to see this? The
Yes.
electronic structure diagram?
Yes, sir.
Okay.
Yes, sir.
Now, when I move this here, you're not able to see it. Now, are you able to see it? Venadocene? No.
No, sir.
Okay, fine. Um, Unfortunately, were you able to see the ferrocene structure earlier? No, you're not able to see the ferrocene structure also. Okay, just hold on for a second. I have to unshare and share again. I have unshared, and let me share screen 2. My apologies. Now you should be able to see. I made a mistake in the way in which I shared the structure. Now are you able to see
Yes,
ferrocene?
sir. It is visible. Yes,
Okay.
sir.
Yes, sir.
Please stop me whenever I say something and it is contradicting what you are seeing on your screen, because I don't get the feedback from the projector like you would do in a classroom. So this is ferrocene. This is perfectly staggered. Okay, you can see the iron atom is in the middle, and the two CP rings are above and below the plane in which iron is there at the origin. So this is one structure, and the vanadocene, the vanadocene is also having the vanadocene is also having a very similar structure. Okay, so what I wanted to tell you is that practically every 3D element in the periodic table forms a metallocene. The stability of the metallocene, however, is not as good as that of ferrocene. Ferrocene is the one which was discovered first, and it was stable up to 300 degrees. And in fact, it is the most stable one. And the explanation that is given for the extraordinary stability of ferrocene is the fact that you fill up to 18 electrons. But notice even here there is a slight hint. Here, for example, we have this dz squared, which is having a bonding combination and a slight. So you have both the s orbital and the dz squared orbital interacting with it. Otherwise, this would in fact be slightly, oops, it would be slightly anti-bonding in nature, because it is interacting with the lowest energy orbital also. So the dz squared, the position of the dz squared has always been a matter of debate, and I will come to it very shortly. But crude, simple-minded calculation gives you this picture, and it seems to hold good for many other species. Now, as I was telling you, ferrocene is the most stable. It sublimes. It can be used for making carbon nanotubes. That's actually another topic altogether. I do not want to get into that now, but if you heat it beyond 300 degrees, it will decompose and it will form the 5-membered rings that are present in carbon nanotubes. 5-membered rings, and it is a kind of a catalyst. The carbon nanotube has got 6 and 5-membered rings, and the 5-membered rings are initiated or seeded with ferrocene. That starts off the formation of carbon nanotubes. And that should not have been here. It's a kind of a aside. If you look at the bond distance between the CP ring and the metal atom, this ring to metal distance That is the shortest in iron. Okay, that is the shortest in iron. If I take one element to the left of the periodic table, so that will give us manganese, MnCp2. Is that known? Yes, it is known, but unfortunately that doesn't really fall into this class for the simple reason that has got 5 unpaired electrons. And if you go back to the this picture, what you realize is that if I have 1 electron less, and if the energy gap between these two orbitals is close enough, then forming a completely paramagnetic system with 1 electron in each of these orbitals would be a favorable system, because you would avoid all electron repulsions in this bunch, in this area. Okay, so it's not surprising that manganese has got MnCp2 has got 5 unpaired electrons. It's got a very large 5.8 Bohr magnetons. Close to it. I'm taking it from my memory, but it's a very large magnetic moment that it has got, but it has got 5 unpaired electrons, and so that's the reason why manganese does not fall in this series. But other species, they have exactly what you would expect for this diagram, and you have no difficulty in explaining the electronic structure. If you go to the left, you populate antibonding orbitals. Antibonding orbitals are populated, and so the distance is larger distance. So iron, cobalt, nickel, and zinc have got larger and larger distances. If you take CpCO2 plus, it should be a stable system purely based on what we have just discussed. CO3 plus with 2 Cp minus, that's also diamagnetic and very stable. Okay, but the moment you have a charge on a metal complex, you tend to have greater reactivity than for the neutral compound, for obvious reasons. It attracts any other molecule which is surrounded by electrons. The electrons are the outermost part of the atom and the molecule. So positively charged species tend to be more reactive. Here, on the other hand, titanium, chromium, etc. are electron deficient, and they tend to react with nucleophiles. So we expect slightly different chemistry on the left side, but nevertheless, all these molecules can be made. If you avoid nucleophiles, then you can make titanium, chromium, manganese complexes with Cp minus. They have very interesting optical properties, very nice colors. This slide just tells you their optical properties, their melting points, and their reactivity. And you will see that all of them on the, except for the iron, all of them are mostly air sensitive. Okay. So they are air sensitive, except for, and that is because they can either give or take electrons, because they have less electrons or more electrons. So they do tend to, yeah. If you take ferrocene itself, it can be oxidized to the 3+ state, and loss of 1 electron from this orbital is no big deal. So you can remove 1 electron. In principle, you can even remove 2 electrons, but then it would become a lot more reactive. So 1 electron ferrocene Fc plus turns out to be a very stable system, ferrocenium cation, and this is more or less, like I said, more or less non-bonding. There is a weak interaction with the lowest energy orbital, but the strength of any interaction depends on the gap, energy gap between the two orbitals which are interacting. The lowest energy Cp minus orbital is buried deep, and the d orbitals are sitting in the valence shell. So this gap is quite a bit. This gap between these two orbitals is quite large, and as a result, the interaction is not significant. So you notice that this orbital is only pushed up slightly higher in energy. So mostly it is non-bonding, and you can remove one electron fairly easily. That makes for Fc plus being a stable cation. It's green in color and it's stable cation. The moment you remove an electron from the ion, Cp is Cp minus. The metal is sitting in the middle and you are oxidizing it further. And so the extent to which the Cp minus is attracted to the metal is more, and you end up with a shorter carbon ion distance. Not only that, you also have a change in the way in which the CPs are oriented. Okay, I can't explain that particular aspect with this molecular orbital diagram. In fact, the CP Fc plus is having an electron not in this particular electronic configuration. Electronic configuration changes when you oxidize it. It is no longer the dz squared above the dx squared minus y squared and dx squared. And the reason for that is often given as the effect of oxidation on the s orbitals and the d orbitals. If you remember, this orbital is mixed with s. Okay, this is mixed with s. S is also mixed with these three orbitals, s, dz squared, and the lowest energy orbital are mixing. Let's go back to the, yeah, here you go. S, dz squared, and the lowest energy orbital. So because of this mixing, when you oxidize the ion, what happens is this orbital falls down in energy more than the way in which this orbital comes down in energy, dx squared minus y squared and the dxy. As a result, the energy system, energy ordering is different, and the electron is present on a degenerate set of orbitals. So this, if you did not follow this, don't worry about it, but this is mentioned here in this slide. Cp2Fe is having the energy diagram like this. On the other hand, excuse me for a minute. Sorry, I hope you're able to hear me. I've unmuted myself again. Cp2Fe plus has 2 electrons on the A1G, 2 electrons on the A1G, and it is the E2G which is having 3 electrons. This is necessary because of the way in which you can do EPR, and the EPR is more consistent with the odd electron being in a degenerate set of orbitals. EPR, Mossbauer, all those spectroscopic methods indicate that in fact the ordering the ordering of Cp2Fe and Cp2Fe plus are different, and so you have this important point to be noted. Fine. If nothing, you please remember that the energy levels of these orbitals are very close. and that is more than important. You will be able to understand uh, all the other nuances if you read specific papers. Okay. The moment you have something different from an 18 electron structure, the structures are no longer symmetrical. Excuse me. Excuse me. So in all these cases, I can adjust the way in which the two ring systems are interacting with the metal by making them unsymmetrically bound. Okay, if I have too many electrons, for example, I can move, let's take Cp2Ni. Cp2Ni has got 20 electrons, right? It has got 20 electrons. And so if I just remove, I can remove 2 electrons and form Cp2Ni2 plus. That would also be an 18 electron system. On the other hand, I can also make it unsymmetrically bound. So I can make it like this, Cp eta 5 and then Cp eta 3 bound to the nickel. That will also make it 18 electron system. So another way would be to make them unsymmetrically bound in terms of the distance between the metal atoms. So Berylocene, for example, has got one short Cp and one long bond between Cp rings. And also these are more ionic. These are not transition metal organometallics, but they are main group organometallics, but still they form sandwich type structures. But these structures, if you remember, the main group can accommodate at the most 8 electrons, and so we end up with ionic structures. Not only that, they are unsymmetrically bound also. Of course, in the case of copper, for example, it's a D10 system, copper 1. D10 system, it does not form a sandwich, but it is forming a half sandwich type of structure, which we will talk about later. Berylocene, the X-ray structure, for example, is a slipped sandwich. Okay, the slipped sandwich is a disordered structure that has been observed for Berylocene. There are 2 positions for the beryllium. One position is here, one position is here. In the book, it is shown as a dotted line, and maybe they should have put a filled circle and an empty circle. So this is the beryllium atom that is sitting in, it can sit in 2 positions, and in some parts of the crystal they are sitting here, in some parts of the crystal they are sitting in a different place. So it's a disordered structure that is formed. You can read one of the, I suggest that you read one of these books, because the variety of structures that are formed with metallocenes is really very large, and it's not possible to note the nuances that are there. Here I have shown for you a polymeric structure, and these are with main group elements potassium and cesium, polymeric structures, and also you'll notice that they are unsymmetrical in some senses. So here is another example. This is again a half sandwich structure. I should not have, I'm going to discuss half sandwich structures later, but let's skip this for the moment. Okay, magnesium forms a metallocene, and this metallocene is again it has got the charge correct. It's Cp minus, and Mg2 plus. So the charge is correct. It should form a nice structure, and it does this unsymmetrical binding because of the fact that it can accommodate at best 8 electrons. So here is another way in which it is unsymmetric. This is similar to berylocene. I think I made a mistake, but berylocene. Okay. So I mentioned to you that manganosine has got 5 unpaired electrons. Okay, and this turns out to be below 160 degrees, it is polymeric, and it has got this structure. Above this temperature, it adopts the usual sandwich structure, and this usual sandwich structure has got this 5 unpaired electrons. Okay. So you can see that the variety is truly very large. If I draw a line, if you'll notice that Cp is eta 5 when it is perfectly sitting in the center of the ring system, and if it is sitting in one of the carbon, below one of the carbons, then it can be eta 1, right? And if it moves slightly towards the ring, it can become eta 3. So if it moves from this position along this direction, the direction in which I put the arrow, then it can become eta 3. And then if it moves a little more further, then it becomes eta 5. So the movement along this line, I think I have this line indicated with an arrow, yeah. And this, along this line, if I move the metal, it requires very little change in position. You can see the delta D that is required is very small, and so metallocenes can be fluxional, or they can easily interact between 2 different states. So let me now tell you what happens when you have indene. Indene would be this molecule, and it can easily form metallocenes like this. And what is interesting is that in many of these complexes, what I told you just now happens very easily. This molecule is in equilibrium, or rather I think I will illustrate this by using this. So what happens is this molecule loses some amount of aromaticity when it goes from this structure to forming an indenyl complex. And the indenyl complex can change between an eta 3 form and an eta 5 form. The eta 5 form loses a little bit of aromaticity. It would have a certain amount of the localized structure. So this loss in aromaticity and this interplay, when it becomes eta 3, then it can gain the aromaticity. So this turns out to be an effect that is observed in many of these complexes. So indenyl complexes, although they are like CP complexes, have got some special properties. Just recently I came across this paper in which cyclonona tetraenyl complex was attempted with zirconium. By the way, zirconium, because of the electron count, it's a D0 when it's +4. Turns out to be something that would coordinate to large ring systems. And when they attempted this reaction, this 9-membered ring, which has got one hydrogen in each of these positions, by the way. So 4 double bonds and one anion. So this ring system rearranged to an indenyl system. And for that to happen, it has to lose 2 hydrogens, and it has lost 2 hydrogens. It was not clear to me from the paper what exactly was the oxidizing agent, but it could have even been the zirconium. The zirconium itself is a good enough oxidizing agent, so it would depend. It would affect the yield, but it would give you the zirconium 4 complex, which has got this structure. Okay, so let me now talk about the fact that we have talked about the closed ring system. Can we make the open ring system? The answer is not very well, because the closed ring system is aromatic, and so it has got extra stability. In fact, the reason why it is called metallocene is because of its analogy with benzene. When Woodward discussed the structure, he said that this is going to have properties similar to that of benzene. And in fact, ferrocene, when it was reacted with Friedel-Crafts conditions, when it was reacted under Friedel-Crafts conditions, RCOCl plus AlCl3, it reacted 1600 times faster than benzene. So it was an aromatic compound. So metallocenes, the Cp minus really functions like an aromatic ring system. Cp minus functions like an aromatic ring system, and that's why this name metallocenes was very popular. So this ring system with these hydrogens are slightly more acidic than what you would expect for an allylic hydrogen. So to make ferrocene, it's fairly easy. If you can make cyclopentadiene. By the way, cyclopentadiene exists as a dimer, and it is usually heated at greater than 150 degrees. Then it cracks. The process is called cracking. It generates, from the Diels-Alder adduct, it generates the monomer. The monomer can be treated with FeCl2 and just triethylamine, and it forms ferrocene. I do not know if I have something else in this slide. Yeah, I messed it up, but okay. So let me erase this. You will. So that's an easy way to make it, but In the laboratory, another convenient way is to make it from thallium. Thallium CP is also easily made and stored. Thallium is poisonous, and so one has to be careful. You have to handle it with care. CpMgBr is also convenient, plus MCl2 will usually give you the compound. CpLi can also be used. So all these compounds can be used. One very fascinating way to make CpLi and CpNa is to use lithium and sodium sand. Molten lithium and molten sodium can be mixed, and they form what is called a sand. They are very fine particles of sodium and lithium, and they will react with the CP ring system and release hydrogen. Now, I seem to have inverted. This is exactly what I told you earlier. I had ordered it wrong. So this is the reaction that I wanted to tell you earlier. That is, FeCl2 is generated from FeCl3 and Fe, and FeCl2 can be reacted with freshly prepared CpH, and the amine, triethylamine, removes the HCl that is generated. I have already mentioned the oxidation. I will continue with the discussion about metallocenes in the next class. And I will stop now because I have overstepped my time. Is there any quick question? Otherwise, we can have a discussion in the beginning of the next class. Okay, so we will continue with the next class. I will stop here.